Students, this is our second video of Elasticity, and today we are going to discuss about the graph of stress versus strain. Okay, so here is your stress versus strain graph. About y-axis we can put stress, and in x-axis we can put strain. So if we draw the graph, the nature of the graph within elastic limit means if it follows the Hooke's law, then we can write stress is directly proportional to strain. Stress is proportional to strain. So the graph will be straight line like this because stress is proportional to strain, and this is called the elastic limit. From O is the origin and the graph up to A, it follow the Hooke's law. Then we can draw it. Suppose if you increasing the stress slightly, then the strain will be slightly increased or more than the previous, and this point we can write B, and this B point is called yield point. What did I say? Yield point. Yield point. And up then the graph C and D like this. So student, like this. Student, we can write this portion is called C, and from C if we retrace the path, we could not retrace the path because the C point, here is the yield point, and when we go beyond B, then the C point is called the permanent stress. Means if you increase the stress slightly or increase the load, then strain will be more than the previous, and then it cannot regain its previous or original shape and size. Cannot regain its original shape and size, and this C point up, if you retrace, we cannot retrace the path, so the CO dash, this portion is called plastic region. Okay, plastic region, permanent stress. Okay, and this portion is called elastic region. Okay, so this is called elastic region, this is called plastic region. So you can draw a long plastic region depending upon the material. Suppose at this point we can write D point, this is called the breaking stress. Breaking stress. So then the wire will break. Suppose you increasing the stress by means of increasing the load, then after certain limit it will break. Okay, so here the strain be more than the previous, means the elongation will be more than the load. Okay, so OA portion is called elastic region, B point is called yield point, means this is the last elastic limit, this is the elastic limit, and beyond B, C point is called permanent stress, this is called the plastic region, and D point is called breaking stress. Okay, got it? So this is the graph, very important graph, stress versus strain graph. Stress versus strain graph. Our next very important topic, which is called potential energy per unit volume. Find the potential energy. Write the question. Find the potential energy of a stretched string. So find the potential energy of a stretched string, means wire, or potential energy per proof that. Another very important question you can write. Prove that potential energy per unit volume is equal to half into stress into strain. Okay, so students, you know, here is an wire. Okay, and this is the hook, and whenever we increase by means of some load, then what happened? Elongation takes place. This is our mg and the elongation is delta L, or we can write small l, and this is the length, original length of the wire. So you know the formula of Young's modulus, y is equal to how much? F by A into small l by capital L. What you need? Potential energy. So you need potential energy or work done, which is equal to force into displacement. Here how much displaced occurred? The small portion delta L. So we can write work done is equal to force into displacement. Force into displacement. Put the value of force from this portion. F is equal to cross multiplying YAL by small l. Put the value here. We get YA capital YA sorry small l by capital L. Okay, so YA small l by capital L. Put the value YA small l into GL by capital L. This is your work done, or potential energy U. You can write potential energy as U. U means potential energy per unit volume. So U equal to this, and you must put integration over here, L dl running from 0 to L. So W is equal to YA capital L, L square by 2, x dx, L square x square by 2. Okay, integration of x into dx, how much? X square by 2. Similarly, L dl L square by 2. So this is your potential energy, or U. Now you are going to prove this is the potential energy for a stress string. That's all. Now you are actually going to prove potential energy per unit volume. So potential energy U by volume. Volume means what? Volume means area into capital L. Area into length is called volume. You know that area of the wire and the length of the wire. Volume equal to what? Area into length. So just put the value. What you have? Y A L square by half capital L, and here area into length for volume, dividing it by volume. So area cancel out. Now just arranging it properly. Half into YL by capital L into small l by capital L. You know student, this is called stress. So U by V is equal to half into stress into, and this is called strain. Okay, so this is called stress, this is called stress, and this is called strain. This is called stress and this is called strain. See student, if you from this line, see from this line, if you write F by area is called what? Stress. F by area, so you have Y into small l by capital L. So Y into small l by capital L is called stress. Understood? So F by A means stress, means this. So half into stress into strain, proved. Okay. So in this video we covered the potential energy per unit potential energy of a stress string, and potential energy per unit volume equal to half into stress into strain. Another topic is the last topic. Remember, Poisson's ratio. What? Poisson's ratio. Students, Poisson's ratio. So what is Poisson's ratio? Right. Poisson's ratio. See student, if you stress it like this longitudinally, if you stress it longitudinally, then what happened? Then it will elongate it like this. These are longitudinal strain. But see, here also you reducing the diameter by delta D. Think. So the original diameter is capital D and you actually reducing by capital delta D. Okay. So Poisson ratio is the pure ratio of, you can write like sigma equal to lateral strain by longitudinal strain. Lateral strain means what? Capital delta D by capital D, change of diameter by original diameter, change of diameter by original diameter. See here, change of diameter, because actually increasing the length by delta L. We stretching the wire, you stretching the wire. If you stretching the wire, then the diameter will be decreased, yes or no? Suppose you stretching the wire. If you stretch the wire, then what happens? Diameter will be reduced. If you stretch the wire, then diameter will be reduced. So delta D by capital B by longitudinal strain means what? Delta L by capital L. Okay, so this is a pure ratio, and if you increasing the length, then diameter will decrease. So you can write minus. So this is the Poisson's ratio. So student, in this video we will cover the Poisson's ratio. Number 1, very important question. Number 2, potential energy per volume. Proof that potential energy per volume equal to half into stress into strain. Very important question. And number 3, draw the graph between stress and strain. Draw the graph between stress and strain. In next video, we are going to discuss the numericals of elasticity. Okay, please students keep studying elasticity. Thank you very much.